Hi everyone. Originally I introduced the magnetic field by mentioning the experimental fact that two lines of current running in parallel will attract one another. Now, we really haven't built that foundation in a fundamental sense. We're really just following the consequences of this one central experimental fact. The interesting thing about this is that we are going to be driven almost without any choice, slowly but surely, to reevaluate the foundation of electromagnetism, Coulomb's law, and ultimately to relativity. One of the first steps down that road is something called Faraday's law. Michael Faraday was very interested in understanding electromagnetism, in particular to see if there was a way to create a magnetic motor. And that was what he spent a lot of his time investigating. He's the one who really came up with the idea of electric and magnetic fields in order to really explain this phenomenon. And so Faraday's law is really about the way in which a changing magnetic field introduces or creates electric potential. Now, this happens as a simple consequence of the Lorentz force law, which also is a consequence of the fact that parallel lines of current attract. You know, at the fundamental level, every line of current are little electrons, therefore each little electron must be experiencing this magnetic force due to its particular motion. Well, Faraday kind of flipped that whole argument on its head and say, suppose I have a wire and I drag it through a magnetic field. And essentially the charges inside the wire, now they're not flowing, there's no current flowing, but they're present, they're inside the wire. It's a conductor, so it will allow the charges to flow. What happens is when I move that wire through the magnetic field, essentially I'm pushing those electrons mechanically, not with a voltage potential, but mechanically pushing the electrons through the magnetic field. Nonetheless, those electrons are in motion through the magnetic field and will experience this Lorentz force. They will be pushed aside. And so in this picture over here, this picture, basically imagine you have this conductive wire here. And it starts on this side of the chart and it gets pushed over here in a certain period of time. You know, say 1 second goes by, it goes from here to here. Okay? The total distance that it travels is given by, you know, just velocity times the amount of time that passes. And basically, as the charges get pushed through the magnetic field, they get pushed up or down based on the right-hand rule. And what happens is, because you have this charge separation, now you have an electric field, electric potential between these two. The charges are separate. They want to get together. They're being held separate because you're pulling it along. Once you stop pulling, they'll collapse back to one another because of the electric forces between them. So this motion is actually inducing EMF, electromotive force, or potential, right? And so it's actually possible to calculate that, and it's given by this very simple formula. The velocity of the wire, conductive wire, times the magnetic field times the length of that wire. This is called motional EMF, and I'm trying to argue now that this is really just a consequence, one more consequence of the fact that parallel lines of current attract one another. So what Faraday realized is not only can we turn that argument on its head, we can also flip this argument and say, suppose I have the wire, but instead of moving the wire, what if I move the magnetic field underneath it? Now that kind of doesn't make sense. What I really am trying to get at is, suppose the strength of the magnetic field, it changes. That ought to induce a similar effect. And that's what's called Faraday's law, and is captured in this formula here. Basically, the electromotive force that is generated by a changing magnetic field, whether that, this is the magnetic flux, by a changing magnetic flux, whether that magnetic flux is changed through motion or through the underlying magnetic field, whenever the magnetic flux changes, the rate of that change is proportional to the electromotive force generated. Now, I just want to remind you what magnetic flux means. We defined electric flux, and this is the same formula. Magnetic flux is just the average magnetic field times the cross-sectional area. So in this picture over here, we've got the magnetic field pointing into the board. That's represented by these little crosses or X's. The magnetic field's going into the board, so the magnetic flux is the total area multiplied by the average magnetic force in there. And that's what this is. And of course, there's this cosine here to indicate we only want to count the direction or the magnetic field that's perpendicular to the cross-sectional area. So when this magnetic flux changes, we get an electromotive force that's generated. One other thing that is interesting or surprising about Faraday's law is that suppose I have this picture here where I've got a magnetic field and I have a ring, a conductive ring. Suppose I reduce the magnetic field, eliminate it. That's going to change the magnetic flux. Obviously, it's going from something to nothing in a certain period of time. What happens is the electromotive force will actually induce this circular current. It will spin the electrons in that conductor. And that is essentially everything there is to know about Faraday's law.